in solar cells, trying to come up with a better mousetrap essentially for photovoltaics. And on this last back part of the bench here, these two of the graduate students are actually doing some work. What? You guys can get closer. Right, and right now there's no problem, right? So this table here, we really measure devices, the actual, solar cells, and check their performance. And what we're mostly interested in is trying to come up with, like I said, the better mousetrap. Because really, if you just look at the basic single gap solar cell, right, silicon or gallium arsenide are essentially two of the best. They theoretically would only, and what it's based on is what the solar spectrum is and how much of the light of the solar spectrum that falls on the Earth can actually be converted into energy. And the thing is when you're working with a semiconductor, then it has a limited ability to convert any part of the sunlight, because there's going to be some sunlight that doesn't actually have enough energy and it would actually just transmit through the material. And then there's going to be the vast majority of it that has actually extra energy. And so most of that extra energy is lost in the form of heat. And so really, the best you can do out of, if I'm just using one material, is around 30% efficient. And right now, in research labs, gallium arsenide and silicon are like at 26 and 27% efficient out of like 30%. Right?
But it's gone way up though, hadn't it? The efficiency of solar panels has gone way up in the last 15 years.
So it's gone up, and and they're out there more mainly because of production costs, right? I mean, so a lot of it has to do with economics also, right? So you have silicon isn't quite as good as gallium arsenide, but silicon is what's being used much more so. Gallium arsenide, there's like no, house panels.
Too expensive.
Yeah. It's just too expensive.
Yeah.
Right? And so what we're really working on is trying to come up with really what is referred to as third generation solar cells, is trying to come up with a method of actually converting more of that electricity. And so you can't just make a simple PN junction, which is what the solar cell is. You have to actually come up with a more complicated design. So multi-junction solar cells are much more complicated design. They're typically just used in space applications, right? But there are multi-junction solar cells out there that are 46% efficient.
Wow.
Right? It just has to do with cost on why they're not really implemented. And so and not all of our work is just geared towards coming up with a new design as far as that goes. Because actually some of the work that we're doing, that these two guys are doing, is really for space applications.
Oh, okay.
Right? And that's where, a lot of times that's where multi-junction solar cells are used, but then other times that's not necessarily what they're going to be used for, because they get irradiated when they're out in beyond the Earth's atmosphere, and that can cause degradation, right? And so we're actually looking at some other materials that are a bit more radiation harm as far as that goes.
Interesting.
But there's sort of two workhorses, right? What we have is a solar simulator, right? And it just mimics what the sunlight is. And we have a reference cell, right? And right now it's measured in suns, right? And actually it says 1.32 suns.
Suns?
Yeah.
Okay.
So the one sun of equivalent
Okay.
on Earth
Okay.
is what we typically are using. But they actually have a filter in here, which is referred to air mass 0, and that's for beyond the atmosphere.
Oh, okay. Cool.
Right? And so
Air mass.
they have that filter in here, and so it reads 1.32 sols.
Okay, that makes sense.
Because it's actually
Beyond.
you get more
Right.
light up there
Mm-hmm.
beyond the atmosphere, right?
Yeah.
So then we have another filter that's AM 1.5, and that really has to do with just so AM air mass, and then 1.5 is actually like referring to like 1 over the cosine of 42 degrees, something like that, and that comes out to be 1.5.
Okay.
And so that is like the standard. So then when people are doing research, they can actually, compare results,
Oh.
right? And so we don't want to, so we're producing electricity, there's an electric current coming. And that's like, and so, this is a silicon reference cell, and so then, it's been like certified so that you can actually put something in there and then adjust the settings so that you can get it right once. Right? And like we have these little wire meshes over there so that they can reduce what the intensity is and mimic Mars, mimic
Okay.
Jupiter,
Cool.
mimic Saturn,
Wow, that's
mimic
awesome.
Uranus, Neptune,
Wow.
by cutting down how much light there is. And then we have, actually, they're working on it right now. Actually, they had a little trouble with the temperature sensor. They have a very small cryostat. It's about this big that we have, like in this dewar right here, there's liquid nitrogen that's at 77 degrees Kelvin. And so they can adjust the temperature anywhere between 77 Kelvin up to actually like over 600 degrees Kelvin.
Wow.
We, for the most part, are just operating between 77 Kelvin and 373 degrees Kelvin because those are the conditions of like the moon under light conditions, right? And essentially at several different temperatures, certain temperatures will match up with those the planets, right? But we also like to really just study the physics as to what's going on. And so regardless of whether or not we were doing work with, so we have a grant with NASA, and that's what, the work that they're doing right now. We have some solar cells that we're going to go up on what's called a very small satellite. It's called a cube satellite. It's going to go out there. It's going to get irradiated, and then we'll measure and see whether or not how it performs.
When is that gonna go up?
Well, I think it's scheduled to go. Howdy, do you know when it's scheduled to go up? The cube sat.
2022, I think the
Yeah.
2022.
That's the tentative date. It's with NASA, right? And then other university actually that we're collaborating
College.
with. What?
Rhodes College.
Rhodes College, right? They have, and they're like, are they building the CubeSat? So like some of the places have actually like made their own CubeSat,
That's the plan is they're engineering.
right? And then we have stuff that's going to go along with it. Experiments get,
Cool.
some of the stuff is just okay, expose it, and then there are things like at the space station, where actual experiments get done. So it all depends on how the grants get written, what's in the proposal, what's going to be done, right? So, and I think in ours, it's actually, they're just going to put it on there, let it get irradiated. There's actually going to be.
No, the big thing with this is that we're actually going to
There's
take
actually
live
gonna be
measurements.
there's
We're taking
gonna be
live measurements.
Okay,
Cool.
Oh, so I guess it's NREL and what they have planned. So there's somebody else that will collaborate.
We're putting
But they were
perovskites and
just-
CAGS stuff on it, so I'm
Yeah.
not going to be doing this.
But I think someone else is just sticking them on there and then letting it, and then measuring it after.
I know some of them are going to get measured in flight, but
Yeah, so I thought that's what ours was. So it's gonna get measured actually while it's on, right? So,
actually, this one harder.
well, go ahead. I can talk louder. All right, so they're just going to evacuate this, and so that way they can cool it down and do, either temperature studies, or they're actually going to do it for particular plant care conditions.
Cool.
So, right, what we do, the basics are light measurements, where mimicking what the sun is, or a dark measurement, we have the lights off, and we want to measure its characteristics in the dark and also in the light. Then we have another basic measurement that's called external quantum efficiency. And we have two other light sources, which we would just send through this monochromator and then selectively pick out the wavelengths. So we would sweep through the wavelengths,
Okay.
go from like 400 nanometers out to 1700 nanometers or less. It depends on what material you're measuring, right? Whether or not it's useful to go out that far. Like silicon, there's really no point going out beyond 1100 nanometers because it doesn't actually absorb any of the light beyond 1100. But we have other materials that have a narrower band gap that would absorb out in that range. And so then you can measure all the way from 400 all the way out to wherever that band gap is. And so you just send the light through, and then there's a grating in there, or prism, and then you can select which light it is. And essentially these are kind of complementary measurements. So we don't want to know just current, we want to know what the current density is. Because I can just put a bigger solar cell under there, and I'm going to get more current.
True.
Right? So that's not really that useful bit of information. You want to know how much current you get out of the specified area.
Current density.
So you just give it by the unit area.